give you a title. So I guess you can call this in your notes vector as a derivative, which ruins the surprise, but at least you know then what I'm doing. So consider a differentiable function which I will call f, and it's of n coordinates, so it's an n-dimensional function. So f of x1 all the way to xn. So a few of you were maybe confused about my notation, but what I mean simply is if you're working in 2 dimensions, then the typical thing is to set x1 equal to x, x2 is equal to y, right? So then f of x1, x2 is just f of xy. So this is a generic way of writing for any coordinate. So just so this may be more familiar. But it's a differentiable function that takes n arguments in, so it's n. Okay. And this function I define on my manifold, which I called m last time, and the manifold has a dimension of n, so up to the function. Fine. I don't know why I started writing on the little board. That's it. Okay. So consider a differentiable function f defined on a manifold m of dimension n. Okay, such that my function f maps m to the real line. So that's my function. It maps m to R. So it's a scalar function. Okay. And further, in this same manifold, consider a curve, any curve, which I will denote as gamma, as you might use in your module. So that simple here is the Greek letter capital gamma. So it's just some curve. And this curve I will define parametrically. Defined parametrically by the equations xi is equal to xi r of lambda, with I goes to 1.
I'm just using the I being superscript instead of subscript.
Yes, always. So from right now, when I put in the upper, I mean the label on the, just the label. Does everybody know what I mean by parametrically? So you did this in polar coordinates, we had an R curve and a thing. And lambda is just my my parameter. So when you do in your second year calculus course, if you remember, when you talk about parameterized curves, you pick a parameter like t or lambda or something. So I'm using lambda to be my parameter. And xi means x1, 2, 3, 4, 5. So you have a set of equations that parametrically defines this curve. Fine. And you've done this in your calculus course because you used to do polar coordinates and R plots and R theta plots and so on. Great. So along this curve, so along gamma, the values of these functions, xi, are given as functions of lambda, which is our parameter, so that the value of f x1 to xn, although I don't need to write that each time, I'll just do it now, is in fact a function of lambda along. So f is a function of x1, x2, x3, xn, but each x is a function of lambda. So this way I actually parameterize the function along the curve. Okay. Thus, we can define a function, or I should say, yeah, a function of lambda, say g of lambda, to be the value of f xi lambda all the way to xn lambda along my curve, which is what I just said. Along. So by picking a curve, any old curve, gamma in my manifold, and assuming that curve can be defined parametrically, I also parameterize my function. Yes? Oh, yeah. So, yes. Okay, so now let me ask you with this g of lambda function, what is its derivative? So, what is dg by d? Any ideas? If g of lambda is defined as f of x of I of lambda, what is dg of lambda? What do I need to use to define it? It starts with the chain. If g of lambda is equal to f of x of lambda, then dg by d lambda is given by the chain rule of f. Right? Okay. So then, dg by d lambda is equal to dxi by d lambda times partial f partial x. Just by chain. And you can see you get it. And of course, if I'm proper, then I should take a summation. So really, it should be I equals 1. Okay, but does everybody understand this? It's just chain rule. Okay. So chain rule. But the point is as follows. Okay. Note that the actual choice of f and consequently g have not actually been used. I've not actually specified in f and a g. So this definition is actually completely general, irrespective to any f or g you want to. I didn't say f should be this and g should be that. I just said there's some f and there's some g. So this derivative then is completely general for any f and for any g. Okay. So, realistically, what I had, if I just ignore the f and g that are there, I have an operator. Namely that d by d lambda is equal to the sum as I equals 1 to n, dxi by d lambda partial by partial. So the idea is this operates on some function, right? So I've left that part blank. Fill in whatever function you want. Okay. So this idea is completely general, this derivative idea. But look what we've done. So, look what we did. So clearly, the curve, gamma, which is a path you can think of in M, determine d by d lambda. So the curve itself in M, which is completely arbitrary, determines what this derivative operator should be, d by d. And does anybody know, if you've taken multivariable calculus, this actually should be very familiar what this is. Think about it. It's a very specific type of derivative. You've done this if you've done very close. So what is the concept related to the gradient? The directional derivative. This is the directional derivative. You see, these are the gradients, and then you have this other component. So in fact, what we have done is the directional derivative along that. Okay. But let me now expand on this a little bit, because it should be clear how this relates to the idea of vectors. So let's do something. So now, but this is the main result, so keep this in mind. Now suppose that there is some other curve. And for lack of a better word, I will call it theta. So one curve is gamma. Now suppose there's another curve called theta. And it passes through some point P. Some point called P. Okay? And pretend now, before, just to keep things clear, I parameterized the first curve by lambda. Now I will parameterize this curve by some other number called tau. Okay. So a lot of Greek letters. And all the Greek people are not here to experience. Where did they go? And this is parameterized by some Greek letter called tau. It's just convention to use Greek letters there. So similarly then, for this one, I can also write down the directional derivative operator. So similarly, I can also write for theta, the following analogous to that, right? So this time I'll have d by d tau as summation I equals 1 to n. Same goes dx by di d tau times partial x. So it's the same. And further, now here's the key point. For any old numbers, a, b, let's say, which are just constants, we can consider the linear combination of the two vectors. We can consider the linear combination, namely a times d by d lambda, which was the first one, plus b times d by d tau. So linear combination of my two. And what do we get if we evaluate it? So if I put d by d lambda, that expression here, and this expression into this one, what do you get? You get the one. So I'll just write out the summation sign. You get a dxi by d lambda plus b dxi by d tau times, once again, this partial by partial x. That is it. Okay, so what difference does that make? every time I have a suspenseful point to make, it gets ruined because I have to erase the board. So you have to wait like 2 more minutes. Which is very strange. But look what we've done here. The coefficients of this are just numbers. dx by I by d tau is just a number. This is just a number. You see that? These are just numbers. So this is just a number. This is just a number. And what I raised before, that coefficient was just a number. So, since the coefficients, you see what I've done here in both relationships, in my d by d lambda, d by d tau here. This is the factor that stays the same in all formulations. But it's multiplied by some number in each situation. So the coefficients of these partial derivatives are just numbers. So since the coefficients of my d by dx i's are real numbers, this must also be a vector. The linear combination. So it seems that this thing I keep writing down, this d by dxi, can be thought of as a set of basis vectors. Very strange that the partial derivatives are actually a set of basis vectors. And you can see the relationship in one. Okay. But if you're confused about this, go back to just standard old linear algebra, and you'll see the analogy immediately. So let me explain. My claim is that these things I've written down on vectors. And my further claim is that these partial derivative things are basis vectors. But you know this, because if I give you some three-dimensional plane and some points there, call it, I don't know, with components dx, or maybe components, let's say 1, 2, 3, how do you write this vector down? Suppose I label the vector v, and this is x, y, z, and this is v. How can I write this equation for this vector?
T plus 2y plus 3z, z 0.
Yeah, exactly. So v is x hat plus 2y hat plus 3 z hat. So you have a bunch of numbers times the basis vectors, right? Same thing. Here's my vector, here are my numbers, my coefficients, and here are my basis vectors. It's the same idea. So this is like your x hat, y hat, z hat, but it's this time disguised itself in terms of partial derivatives. It's the same thing though. It's exactly the same idea. I have some vector, here are my coefficients of my 1, 2, 3, and my basis vector. So that's the analogy. But anyway, because remember, we're not in linear spaces anymore. We have curved spaces now. So we should expect something very different than what we've seen before to talk about vectors. And it turns out the idea that these partial derivative operators should be basis vectors instead of x hat, y hat, and z hat is interesting. But anyways, these things here are elements of the vector space at my point. And there are precisely n of them, because that's the dimension we are in. And I can prove to you, but I will not prove it to you because it's a trivial proof to you, that each one of these vectors are linearly independent. So therefore, Because they're linearly independent, there's n of them. I can therefore write any vector, say d by d psi, as a linear combination, just like I did with my three-dimensional plane. As a linear combination of these basis vectors. And the coefficients of each vector now are just these numbers. With coefficients, just given by dx1 by d psi, all the way to dx and so that's our generalization. Instead of ax hat plus by hat plus cz hat, now I have these derivatives, and the x hat, y hat, z hat now have been replaced with these partial derivatives. And it's very easy how we got these because it's just using chain rule on some arbitrary curve. That's where we started. So therefore, what have we done? We have defined our vector field on our curve space. This is how you do it. Yes?
It's kind of like it's similar to like the adapted, like the technical on the
Exactly. I was gonna write.
Okay, that.
No, it's good. That's precisely good. Is there a question?
Yes, I have a question.
Yes.
So what lectures feature the power series?
Power series.
Yes, because you said we didn't need to do all of lectures.
I don't know. I think it's. Did I write down a power series? No. I think it's somewhere in the middle, 13 to. Okay. Yeah. I think it is. Nice question. I don't know. Okay. I don't know. That's just okay. So therefore, we have defined a vector field on M. Why isn't anybody excited about this? Maybe you've not observed it. So that was our task. We said we wanted to define a vector on some curved space. We just did it, and nobody is impressed. It's okay. So does everybody understand what I'm doing so far? No. As long as you understand that these are the coefficients and my partials are my basis vectors. But let's see what that means. So let's do what Gates is saying. Okay. In other words, the directional derivatives at a point is the manifold version, for lack of a better expression, of a, say it again, tangent vector. That's what we've really done. These are tangent vectors. I'm taking the derivative along curve, so it's tangent vector. So the directional derivative at a point, what we are doing is the manifold version of a tangent vector.
Sorry, Professor, can you explain about the manifold? What is the manifold?
So 3 classes talking about manifold.
Yes,
It's just, if you want a long story short, it's just a collection of points. A general collection of points, that any local region of that looks like our area. Okay? Well, you scared me for a second to maybe think I had not talked about manifold. I was very scared, but I didn't. I remember I did it. Okay. Okay. Now you can imagine that at any point, remember, so all this is defined in the neighborhood of some point P. At this point P, you can have many tangent vectors. We have 10 of them at any single point. And so at any point P, you have n tangent vectors if you have a linear space at some point P of these vectors. Okay? So, therefore, we say that the set of tangent vectors at my point P defines what we call the tangent space. And I denote this tangent space by the following funny notation. T for tangent space. P for being the tangent space at that point P as a function of M. That's the thing. So at any point, you have a set of tangent vectors, and the collection of those tangent vectors form a tangent space, as you would expect. A collection of vectors forms a linear space at this point.
So it just holds in the neighborhood of T?
Exactly. And that makes, keep that in mind, yes, very good. So it's a local definition. Yeah. Oh, but then, which is what you alluded to, this tangent space is just defined within some neighborhood of one point, P. But I have millions of points in my manifold, infinite many. So what do I do? How do I combine this? Well, at every point P in M, so many points P in M, we can define a vector space. So that's my TP. I'm just rewriting it so it's clear. And further, the union of all of these possible spaces over each point P is called the tangent space of M. Or, which is the more commonly known notation, is called the tangent bundle. Tangent. And we denote this simply as T. And it's defined, as I said, as the union of all possible tangent spaces. So defined as union P. So just work it out in your head. You have a manifold, which is some general space, could be curved, whatever. You want to talk about vectors. So at each point at this, I define a vector space, which is a collection of n tangent vectors at each point. But I have many points, so I have many tangent spaces. Right? So think of your sphere once again. You'll have some tangent space there. You'll have some tangent space there. You'll have some tangent space there. And so, you have infinitely. And the collection of all these then is the tangent. Very good. So that's my little summary of the differential geometry you will need in this course. But now, any questions on this? So I cannot go too further with this. It's because ironically, you need to understand differential equations to go further than this. So it's a very weird duality. I need this to understand differential equations, but I need differential equations to understand this. It's a very confusing point we're at right now. But does everybody understand so far, more or less? Okay. So now how does this then relate to the nonlinear dynamical system? So let's go back. Let's go way, way back. But now you know all this. So if I give you an exam on these questions, you'll be able to do it, right? Don't joke, I may actually do it. No, I'm not. No, the final exam. These could be the thinking questions I was hinting at. Yeah, like one question could be, give all possible charts of a Mobius strip or something like this. No, I will not do that. Maybe. Okay, so let's go back to dynamical systems. But now we know that this is our general space of which these systems are defined. So back to dynamics. I will just write DS. I don't want to keep writing on dynamics. Okay. So, if you've forgotten what a dynamical system is, let me remind you. Okay. So we wish to study systems, maybe they're physical systems, where the state of this system at time t, let's say, can be described by an element or point, for better word, of M, which is our number. And in other books, I believe when I was doing linear systems, I called M state space. So it's your manifold is the state space. It's just a collection of points. So we wish to study systems where the state of the system at time t can be described by an element or point plus time, whose evolution is governed by an anonymous or autonomous set of differential equations on M. Where we wrote, if you remember, dx vector for dt. So x is a vector of the point. Equal to this arbitrary function. And further, now I can tell you where all these things are defined because we know now the background geometry. Where my function f is a mapping that goes from my manifold to my tangent. Because these are vector fields, remember? My goal was, if this is on some general geometry, how do I talk about this now? Now I know. My vector field must be a function that goes from M to T. The tangent space, or tangent mode. Which assigns to each point, call it M, in my manifold, a vector in T, M. That's how I can do it. For this course, though, I must now stop here. I cannot go further than this because we need more partial differential equations and Riemannian geometry. So for the rest of this course, we will consider where my manifold M is actually Rn to make life simple. But it turns out, first of all, two things. Everything we have done generalizes to either case. So everything I will write now in the future will work for M. And furthermore, it's easy to do it. And 99.9% of dynamical systems can be completely described in Rn. You don't have to go too much. You can. Sometimes it's more helpful. But everything we will do will be completely general. So, if M is equal to Rn, so M is in fact just the Rn space, what is the tangent space of Rn? Very simple. So if my manifold now is Rn, what is the tangent bundle of Rn? Very good. Why is it? Did everybody hear that?
No.
Okay. If Rn is just the space you're dealing with, then what is the collection of tangent vectors to Rn? It's just another collection of vectors. Yes? So therefore, I can take f to be a function. It goes from Rn to Rn. So that will help me a lot. Okay, good. Okay. So, if my function now is just defined from Rn to Rn, so therefore I can cover both the poles. So my vector x then, which I've been writing in the dx by t of f of x, is just this term, x1 to xn. It's just a collection of points. And yeah. So you can imagine now what this evolution law is saying is you have a vector described by these coordinates, and this tells you how that vector changes in time. Hence the differential equation. But because it's n-dimensional, you have n of these equations. So a system of differential equations. Okay. So for, I will use either notation, but sometimes, in fact most of the times, I will just denote dx by dt as simply x prime. So you don't get confused with it. Or x dot x prime. All mean the same. Where x, of course, is a point. N-dimensional vector, or collection of points. Okay. And furthermore, my vector field, which is also a function from Rn to Rn, is just a collection of x. So something f1 of x all the way to fn. So that's what I've been meaning by vector field. Okay. So now we can extend this definition. As follows. So there are some special types of dynamical systems. One we've been already doing, which is the linear. So just to give you some more introduction, there are special types of dynamical systems. The first one, which we did already, was with f was just ax, so linear. So where f of x is just some constant matrix times x. This is our famous linear system. So if you remember, we wrote down x prime is equal to 8x. So that's one possibility. There's another special class, which are called gradient dynamical systems. And this simply occurs if f is a gradient of some scalar field. minus del z, where z is my space. So you've seen this in your multivariable calculus. So if you have some special f that's written like this, which is the gradient of the scalar field, this is a special type of diamond called gradient diamond. So in this case, you just have x prime is equal to minus del z. So non-linear. And you can also have a further one, which I will not get to because it's not a physics course, but if this was the previous course, I would do this case. But they're called Hamiltonian dynamics. But I will not go into any further details, although I really wish I could, but I don't. It's actually very much related to a lot of the stuff we're doing PDs next year, but I don't want to go too sideways. Okay. So those are just some examples of dynamics. So let's go now more into, if I give you a dynamical system, a nonlinear one, what do you do with it? How do you actually do something with it? We've done a lot of theory so far, but I've not actually told you how to do anything with these systems, which is often how it works in math courses for some reason. Anyway, so you can kind of start that, and then I will finish next week. Okay, so some basic So, we want to solve these systems of equations, so what does it mean to have a solution? So basically, a solution of the dynamical system, x vector prime is equal to f of x, on Rn, so instead of m I'm specifically doing Rn, is a function which I will denote by psi, let's say, that goes from R to Rn, which satisfies phi prime of t is equal to f phi of t. So, if you want to solve this differential equation or system of equations, and your claim is that the psi is the solution to this, in other words, x is equal to psi then should satisfy this equation, right? And if it satisfies this equation, then therefore psi is the solution to the other question. Okay, so all these are connected. Oh yeah, and this is the most important part, for all t, so for all time. It's a technical point though, as you saw in the single dimension ODE space, maybe it's not possible to find a solution for all time. And we'll talk about that in a second. So this is a caveat. It could blow up or something like that, as we saw in the linear first order. So that's what you mean by solution. What else? What else can we say? And since, oh yes, and further, the image of phi of t in Rn is what we call the orbit of the dynamical system. So by image, I just mean a picture of this. So you solve this dynamical system, you'll get a parameterization of a curve of phi of t, and the sketch of those curves in R2, R3, or whatever is what we call the orbit. It's just being drawing like this. It's called the orbit. And further, carefully at this relation I've written down in the box. Since phi prime of t is equal to f of phi of t or psi of t, what am I saying? I'm saying that the vector field f is tangent to my solution. F of x is tangent to the order. So those who have done electromagnetism know the relationship between the gradient of the field and the tangent and all that stuff, the solution. Okay. So I will stop here, and next class I will talk about very briefly existence and uniqueness.
No. I think it's getting worse every day in terms of what I'm understanding. I didn't.
One of you wants the email.
All they do is literally just break it up. You just simplify it, simplify it, simplify it.
Hey, can you do that on your own?
Probably, well, given enough time.